introduce the talks to start off the session.
Thank you, Alex. And I really need to say that the three talks of today are really, really interesting, and I think that they touch very closely to our interests as Alife and society group or emerging group, right? So I just don't want to delay this anymore. So I'll introduce. We have three presentations, as I said before. The first presentation will be given by Penny Faulkner. It's a work that she developed with Susan Stepney and Jasmine Mirali. Their talk is called Socio-Physical Modeling and Declining Mobility. Then after Penny's presentation, we'll move to Nathan Brooks' presentation, which is a work with Simon Powers and James Ford. And the name is Mechanism to Promote Social Behavior in Household Load Balancing. And finally, we'll have a presentation from Hiroki talking about extreme ideas emerging from social conformity and homophily, an adaptive social network model. So I'll say Penny to present her work. Thank you.
Thank you very much. Let's just hope this works. There we go. Excellent. Hopefully everyone can see that. So I can't remember if this was the older title, but socio-physical modeling, which is basically simulating situated agents in a complex environment, and we're modeling it as a dynamic network, which is a lot of words, and we'll unpack it as we go. But the focus of this, as with a lot of what's happening in this session, is complex systems and people. So agent-based modeling, it was the start of this work, and obviously it's absolutely great for modeling stuff involving people. Social systems rely heavily on the cumulative result of lots of individual interactions, and agent-based modeling simulates that very well on a large scale, and it's easy to parallelize and distribute. One of the small drawbacks of it, though, is individuals don't exist inside a single system. We exist inside lots of systems, and that's one thing that's become very painfully obvious in the current situation. Our education, medical, transport, the economy, it's all tied in together, and it all influences each other. And drawing the line around the system we're building can be one of the biggest challenges for any sort of modeling. So what have we done that's in any way different? So most classic agents, you've got world and it's inside their heads, and we've decided that we wanted to take more out and give them a quite rich environment. So we're modeling that as a dynamic graph. And one of the big parts about this, though, is we've not just put them on a graph and situated them. The graph itself actually takes over some control from the agent. So we've separated out what the environment defines the agent capable of and what the agent defines itself capable of. The equivalent thing would be if you're driving around a roundabout, there's a difference between a road being closed, and so it's not available to you, and you eliminating a road from your decisions because you have no idea where it goes to. And in most agent-based models, that distinction is very hard to determine because it's all one set of code and it all does it at once. Whereas here, either the agent has that option or they don't. When it's handed to them, we can really separate where the agent doesn't think something's possible and the environment says it's not possible. But probably more for this session, so what did our overall goals for this work were to build models where we had that kind of separation and stuff, but also that agents would be able to be in multiple environments. This helps us deal with not necessarily having to draw those lines in quite so solidly. So this allows us to have agents in a physical environment, but also a social environment, maybe a digital environment, an economic environment, by having multiple networks that the agents can be situated on. And we wanted those environments to be dynamic, not just to react to the agents, but to react to outside forces and to change on their own, even without the agents, because that's the reality of the world. As an individual, my options change even if I do nothing. And even if the people around me aren't doing much, the world still changes. And as I've already said, one of the important parts was being able to separate effects and changes on the environment and agents from one another, because that can make it a lot easier to draw implications from our results, because we can be a little bit more certain which way round things went, and if we can separate environment and agents a bit more. And one of the really important parts that we'll talk about a bit more as we go on is a clear path between experts and the modeling of the situation, the systems as they see it, and the modelers' platforms, and what we actually create as simulations. So how have we gone about that? Mostly by deciding we needed more models. We decided we needed a lot of models. I think we started with 4 and ended up at 7, and I wouldn't put it past us to add some more at some point. But the 3 big parts about this is this top level common meta model. That's really huge for this. It means we've got the concepts of agents, of nodes and edges in our environment, of all of that sort of stuff as one concept, well defined, that everyone is feeding from. So we're not suddenly deciding we need other elements. We're designing everything to one meta model to make it easier to communicate between our different models as we go. We've also separated down this bottom level into 3 parts. We've got a domain model, a platform model, and a simulation platform. And this gives us the domain model, which is what the system looks like to the specialist. So that's our domain expert comes in and they tell us in the language of our meta model what their system looks like, which we then can translate into something that fits into a platform model, which draws a line around what we're actually going out of that broad idea of the system, what we're going to try and simulate, which we then implement as our simulation platform. And what this allows us to do is create a very clear and close communication between domain experts and modelers. And that's been very important to us through this whole setup. Finally, we've got this middle layer, the frameworks. And this is also quite important because it means we can build this very generic meta model. We can build very specific domain models and simulation platforms, but we can do all of that a little bit quicker because in between those, we've got these frameworks that we can build up and then specialize downwards. So we can have a concept of, say, medical models, a rough starting point to work with there that we can specialize down to a domain model for a particular use. We already have the beginnings of a simulation framework. So we have a package of code that we can specialize into a particular model to help us do things a little bit quicker, but also, again, it helps keep everything a little bit more consistent and make it a little easier to talk across those lines. So we'll just take a quick look at the meta model, because that encapsulates what we're working towards with the whole setup. So one of the main parts of this is player. We have nodes and agents, and those are 2 active parts of our system, and they're joined up by these connectors. So agents would be connected to a node by, in particular, a located edge connector, telling us where that agent is in a network at any time. We'd also have connectors between the nodes and the network telling us how those nodes communicate or how agents can move between them. And they're all players because they all have roles and they can have multiple roles, and roles just mean they act and they have internal state, which means they can remember things. And when we say they act, it means they can affect things around them. So they can trigger events which other things handle and react to. And the main reason for having this concept of an event rather than just actions is it allows us to bring in these last two who are objects, the intervener and the viewer. The intervener allows us to again blur those lines around our system by allowing us to introduce extra change into the system. For instance, if we're working in a transport network, we want to be able to say, have weather events occur in our system and affect our transport, but we don't want to simulate weather. So by having an intervener, we can just trigger that event in the system. We don't have to worry about it. It also allows us to do some more interesting stuff, like change the structure of our network at runtime. It allows us to trigger, say, policy change happening in our system, either in a reaction to something that's going on in the system, or at a set time, however you want to set that up. And finally, we have the viewer. This, again, helps us to connect to domain experts in a way. By having a designated system of how we look at our system, we don't just look at the whole thing, we make sure we also have a designated what we are looking at, which means we can draw out information to match up with real world data sets and with real world perceptions of what we can look at the system the way we would in the real world, I think is the main point here. And so we can actually look at that. And because we do actually have access to all this more detailed data and we do actually have the full run, we can also look at reality versus what we'd see in reality. Okay. So that's the meta model. And that's been fed through, and we've got the beginnings of this simulation framework I mentioned earlier. That's available on, the code's available on GitHub, the documentation's available here. It's a work in progress, but it was used and is actually the backbone of our case study. So we do have a small toy case study that we've already implemented that you can see in the paper, and that's got some details and results. It's a toy system. We've only got 7 nodes in our environment there. It's just simulating some basic concepts of what happens to people with declining mobility and what options are available to them. But it does actually filter on the nodes quite a lot. So we have a lot of steps where the nodes are defining what's available to an individual with declining mobility before the individual even gets a choice. And there are some results relating to that, and we did find some small effects. And again, you can see those in the paper, and the code and the documentation are all available. But we're more interested really in this whole idea of socio-physical modeling today. So as a quick step through, here's how we the sort of dynamics we can capture in these systems. So we can change our edges in our network. As our agents move around between our nodes, our edges can change. This can record busyness or number of agents traveled or anything really, and it can change back. And this can just keep happening. We can also add extra population and diverse population with different roles or different types of agents. And we can lose them, and agents can change. So agents can add roles or lose roles over time. And maybe those new roles mean we get even newer roles that we've not really expected before. But the big part is we can add structures, and this can all happen at runtime. You don't need to reinitialize. The system can just add an extra part to the graph. And maybe when we do that, everything keeps moving around, but we get another new sort of agent because we've got a new bit of the graph. And maybe these ideas spread to the rest of our graph as we go. But I did promise you multiple networks. So this is a social network added to our system. And here the nodes and the agents are linked. So this actually follows our agents as they move. And that means there's now their physical location, but there's also social dynamics happening here as well. Now, just adding to that complexity capability. And this is all about capturing these dynamics and allowing us to use them out in the other side of the dynamics, which is our workflow and how we work together to develop these models. So we've got the simulation platform and the domain model, both feeding back into developing further our meta model and our frameworks, in particular our platform framework, so that we over time get a clearer idea of what these models should look like and what concepts we need in that meta model. This platform model is co-created by the domain expert in the modeler, and that's very important. And that's an ongoing co-creation. It means as the modeler builds the simulation, they show what they're doing to the domain expert brings what they've been seeing in the real world in and says, how is that going? Is that looking correct? And you revise the platform model. You maybe change the boundaries of your system. You might contract it, you might expand it, but it changes all the time in this linked co-creation. We've got the classic feedback from our simulation to our domain model, changing our simulation and hopefully driving that process. And hopefully once you've developed all of these to a sufficient level, you're taking your simulation platform and you're feeding it back into the domain model and using both the domain expert and the modeler to hopefully influence policy recommendations. And it's important that you have both the domain expert and the modeler here, because your domain expert can give you the inference from the model better. What does that mean in real life? But you want to keep your modeler around for this as well, because someone needs to keep reminding everyone of those abstractions that the modeler has made. All those things they've assumed, all the things they've ignored, and the limitations and errors of these systems, because they're not perfect. If the model says it, it might be true. And it's important that that is part of the policy recommendation process, front and center. So we're hoping to extend this. We're currently working on multiple networks, multiple agent types and role systems. We're currently adding in social networks that combine the agent and node. We're moving into models in different domains and models based on real data. Right. Thank you. I guess this is where I look at what's been happening in the chat.
Okay, thank you, Penny. Well, I guess, does anyone have any question? I think there's some here in the chat. Well, if you're okay, I can start with the questions we have here in the chat, Penny.
Mm-hmm.
And I think the first one is from Harold Fellerman. He's asking, would you know how your approach differs from a process algebra such as pi calculus?
I think the underlying simulation might have some similarities, but I think, as Susan says, part of this is about developing not just that side of things, but also this much broader event structure and model structure beyond just the model itself, but these frameworks and the meta model as well. And as Susan said in the chat, we've also these events which we're slowly eking our way towards that allow us this intervention side of things and allow us to really provide greater complexity without necessarily expanding what we're modeling directly.
Thanks, Penny. That's pretty clear. It occurred to me though when you presented that a lot of those events and interactions, it's very similar concepts and they use in process algebras, and you could describe the agents as well as the environment as interacting processes. So maybe this community has already solved some of the things, and you could look if there is some things that you don't have to reinvent the wheel. But granted that, for example, your graph framework would be something on a higher level that you would need to then implement in any of the formalisms.
As I say, the graph side of things is fairly central. It might be similar, but we're not really focusing on the sort of low-level side of it that way. I've been mostly looking at the software side, so this is actually implemented using multiple Python processes interacting with a database. I don't really want to work out what the mathematical stuff is around that, if I can help it. But yeah, certainly on certain levels, it probably does closely align with some work that's already been done. We're not trying to reinvent agent-based modeling with this. We're just trying to work out how we can expand it and add more.
Not just meant for, there's some tricky things with concurrency and deadlocks and things like that that have been analyzed day in, day out.
Most of that's actually been avoided. As I say, we've separated it all out and it interacts through a database. So our agents, it's all been done with, what's the term? Environment orientation. Our agents don't actually directly communicate with each other. It's all through the environment. So each agent functionally has a node which stores its social information. When other agents want to interact with it, they're interacting with that node. But all of this is just in the database. We could theoretically run everything on a separate process, and it's all the communication goes through the database.
All right, thanks, Penny.
That's okay.
Okay, I guess we have another question from Hiroki. So,
but there are two other questions that are ahead of me, so you should take those questions first.
Right. Yes, I think we've got a concrete model implemented in this framework.
I think people can unmute themselves and say their questions in person, because that might be a bit more human as well. So, I mean, maybe Oscar, do you want to give your question?
Yeah, hey, can you hear me?
Yep.
Yeah.
Yeah, I mean, I'm new to all this, so I was just asking for some examples that, you know, you model with this and what kind of results you got.
So we have a toy model that's in the paper if you want to go and look at that. We're hoping to get hold of some real data and that to do some more complicated models. The kind of data that's needed, part of the idea of this process is the domain, we talk to the domain expert and we decide what we can model with the data we have. One of the problems I see with a lot of these modeling setups is you decide the model you want to build, you build the model, and then you go, can you give me the data so I can validate my model? And the domain guys turn around to you and go, nope, doesn't exist. We can't get that data.
Okay.
So part of the idea here is to set up a system that allows us to validate with the data we have. So one of the things that viewer does is it allows us to take results from our system that match what we can get in the real world. So if all we have from the real world is survey data, we can survey our system in the same manner, and we can try and train our parameters till those two match, rather than us going, I'm going to need the absolute numbers for this, that, and the other to domain experts, which they're not going to be able to give us.
How would you, if I can have a quick follow-up, how would you tune this system in practice? So let's say you put in your data, you get some results. Now something's not, you know, meeting your expectations. Like, how would you debug this?
Depends what our expectations were, whether we think it's a problem with how a particular node is set up. So our nodes will attempt to operate like different things are in RES. So our current example has a hospital node. Initially with that node processed agents. It took a set amount of time and caused a set amount of mobility decline in our agents while they were stuck in hospital. We later changed that, so now they have a normalized distribution on how long they'll be there, and given how long they're there, they receive a normalized version of mobility decline, which means some of our agents are there for quite a long time and others are there very short times, and we're hoping to improve that with the social network such that the time they're stuck in hospital starts to relate to their social contacts, which is a little bit closer to reality. And it's things like that. We'd have to consider any debugging on a case-by-case basis, because it could be how the agents are making decisions, or it could be how a node is functioning, or it could be the interaction of the two. A lot of it's going to be, we come back to where do we think the problem is? How do we get that part closer to reality? Because maybe at times what we might see as a bug is actually something that's happening in reality that just doesn't get picked up.
Okay. All right. Thank you.
Can I just add something in terms of the kind of the motivation for this? So it's kind of taking it away from the technicalities, because you're asking about examples, and the kind of whole motivation comes from the policymaking domain, where the original idea came from this notion of the old and frail people. If they have a fall, they don't get rehabilitated enough. So the kinds of things we want to do with this model eventually, once we've got the nuts and bolts sorted out, is to look at problems like, if you're doing a policy intervention, supposing you consider rehabilitating people who've had falls, then how does that play out in the long term? And currently the models that are being used for such things are very much like system dynamic models that have seen structural stability of the social system. Whereas what we wanted to be able to do is to say, if you make an intervention, the system at time t is different from the system at time t+1. So how does it change? And the way that it changes is kind of place-based, right? Because different agents have different resources and so on. So at the end of the day, this kind of brilliant thing that came from Penny, which is about taking the world out of the agent's mind, is because you're able then to look at one of the things which is a great policy challenge, which is how do you do kind of not one size fits all, but how do you try to design things which are sensitive to agent context and agent resource bases, so you get the best bang for your buck for whatever you invest. And things like early interventions for rehab are costly and therefore not done. But if you look at how they play out over the lifetime of the elderly population, it may actually turn out to give you quite a nice number as far as the policymakers go. And that kind of thinking hasn't been done.
Okay, I think Hiroki had a question. I think, oh no, Simon. Simon, I think, was next.
Simon, go ahead.
I just wanted to check my understanding of the meta model. And I think this does link actually a bit to Hiroki's question. And it seemed to me that in some sense what the role of the meta model was to create a common ontology of terms and concepts that's going to be used by both the platform model and the domain level. So the kind of meta model is really about setting up what your ontology is and the ontological knowledge that you're capturing. I'm just wondering if this was a view that you'd thought about.
Yeah, no, absolutely. One of the biggest challenges with anything like this is, and we have enough discussions about this ourselves, is common language. When I say node, I come from a mathematics background. When I say nodes and graphs and things, I have one particular view of it. Yasmin had a very different initial viewpoint, and we've had a lot of discussions trying to work out what both of us are thinking of and what we mean when we're talking about these concepts. And I think that's one of the reasons we get such a domain expert tells you about the system, modeler goes away, models it, comes back and gives results set up these days, is because this sort of co-creation part is very challenging when you don't have common language, a common concept of what you're looking at. So yeah, the idea of the meta model is it gives you, these are the things we have to play with. These are what we call these, and this is what we mean by these words. So within that, this is how we want our setup to work and how our system to work. Moving a little on to Hiroki's question, when you do get into the point where you have a real mismatch between the two, then we start looking at, well, is the meta model sufficient? Is are our current model frameworks sufficient? Because we've definitely also had moments like this, just with as far as we've got so far, of going, we need another concept. We need a new thing in our meta model because currently we can't capture the X. And yeah, it does mean you also spend a lot of time reaching conclusions about what you want to call things and what an agent is and what a network is and environments. And it just takes time, and you just have to commit to having those discussions and occasionally having them repeatedly. And it's not that anyone in that discussion is not understanding anyone else, it's that none of you are being clear enough yet.
Yep.
And I think that's the attitude that gets you where you want to go with it.
Yep. Thank you.
Well, I think that we use our 10 minutes for question and answers. Maybe we should move to the next presentation. Is that okay with you?
Yeah.
I would invite Brooks to present his her work, right? Yeah, exactly.